Okay, let's take a look at question 2. So we can see straight away the question 2 with this setup that we've got here. This is going to be our specific heat required practical. So this is one of the required practicals that we have been asked to make sure that we are aware of for this exam paper. So we are given a setup. Importantly, just sort of looking at it, we're using a joule meter. I think the joule meter is the best setup for this because what that means is that you don't need to calculate the amount of energy input yourself. You can just get it straight from this device called the joule meter. So here's the method. Put 200 grams of oil in a beaker, record the temperature of the oil, switch on the heater. After 5 minutes, record the temperature of the oil and the reading on the joule meter. Repeat steps 1 to 4 with different oils. So it's a classic method, so we're probably not going to be able to be asked to write a method. So let's see what we're asked. Give one variable the students controlled. Okay, so a control variable means keep the same. So we're looking for one thing in that method that they kept the same. So you control variables in order to make sure that your results are reliable. So look, so they said each time put 200 grams of oil. So that's something they kept the same each time. And also they said 5 minutes. So they were going to turn the equipment on for 5 minutes and then record it. So either of those is fine. So I'm going to say this one here, which is the mass of the oil, but you could also have the amount of time the equipment was turned on for. So give one variable is the mass of the oil, and in this case it was 200 grams. The table shows the student's results for one oil. What is the resolution of the thermometer used? Okay, resolution. The word resolution means like the smallest units. So in this one, we can see that we've got a 21, we've got a 68. It would be reasonable to expect that we might get, 67, or we might get 24, or we might get a 48 or something like that. It wouldn't be reasonable to expect that we would get 42.4, because there's nothing in here with a decimal place. All of these are going up in ones, and that's what it means by resolution. So in this case, they're all going up by 1 degree. You wouldn't expect to go up by 0.1 of a degree. So I'll take those off. So resolution in this case is 1 degree Celsius. Students calculate specific heat capacity of the oil as, highlighter, 2,100 joules per kilogram degree Celsius. The correct value for specific heat capacity of the oil is 1630 joules per kilogram degree Celsius. Calculate the percentage difference. Okay, percentage difference is something that if you read exam reports, and if you're a science teacher like I am, you do, you see that students often get this wrong. Very rare that students get these right. So let's break down what percentage difference means. First off, it's the difference between the two results. And then we just turn that into a percentage based on any of the other results. Normally the starting value. So you can have a percentage increase or you can have a percentage decrease. In this case, we're just looking at a difference. So let's have a look. So we first off just find the difference. So to find the difference, we're going to take the value of the student calculated, and we're going to take away the actual. Okay, and if we do that, we will get, let's check it. All right, don't do it in your head. Always grab your calculator, no matter how easy you think the sum is. I'm not saying this one's easy, but this won't be the type people attempted. Okay, so we've got 470. I'm going to leave my calculator up because of what we're going to do in a second. So we've got 470. That is my difference. So in order to get the percentage difference, what we're going to do is we're going to we'll use this difference against the correct value. So like with any percentage, we want to try and get a number or a decimal when we do our division that's less than 1, and our full number should be less than 100%. So to do that, we're going to get 470, and we're going to divide that by our correct value, which is 1630. So if we do that, 470 divided by 1630 gives me 0.2883. That'll do. If we just do that to 2 decimal places, we'll get 28. But we should turn it into a percentage first. In order to turn that into percentage, we just get the answer. We're going to times it by 100, which gives us 28.83 as a percentage. 28.83. So we'll be 1 decimal place. So that doesn't round that up. So we'll say our percentage difference is 28.8%. You could also have gone the other way. You could have said 470 divided by 2100, which is the student's value. 470 divided by 2100, and we could have had 22%. 22.4%. That would have been fine too. It's because they're asking for a percentage difference. They're not asking for a percentage decrease or a percentage increase. So it doesn't really matter which one you calculate the percentage from. So there's 2 improvements the students could make in order to obtain more accurate value for the specific heat capacity. Okay, so we're going to more accurate value. So we're going to have to look at their method, and we're going to see where there could have been possible errors, like why have they got the specific heat capacity 28% wrong. So here's the method. So in this practical, hopefully, if you've learnt it, you'll realise that most of the errors come from heat loss. All right, we tend to find that the heat loss to the surroundings, because if we use our formula, which is that the change in energy equals mass times specific heat capacity times by your change in temperature, what we're saying is all of the energy goes into changing the temperature of the oil. But in reality, with this setup, some of the energy is going to be lost as heat. So our value for specific heat capacity is going to be wrong. So we have to figure out, that's 2 suggestions of how we could reduce the heat loss. Well, the first thing, we could stick a lid on this beaker. All right, so if we put a lid on the beaker, that'll stop the heat loss, or at least some of it. So we could place a lid on the beaker of oil. So there's one way. We could also insulate the beaker. So we could put insulation around it like that, which would stop heat coming out. But that's quite similar to saying putting a lid on. The other probably big error with this is that a lot of your heater here is sticking out the top of the oil. So it's going to be heating the air directly rather than heating the oil. So we could use a smaller heater, or make sure that the heater that we use is fully submerged in that oil. So we'll say that's our second point. So we'll say use a smaller heater which is fully submerged in the oil. Okay, there are 2 ways to make that more accurate. And then the last question, a company is considering what metal to use to make saucepans. They use data about the cost and the specific heat capacity. It's just 2 other, all right, so we can't use the same properties, and properties are like, things about it, characteristics of it, of the metal, that the company needs to consider when deciding which metal to use. All right, well, so for this one, this is one like a real life type question. There's nothing that you could have learned in science about this. It's just linking it to things that you might know. So if you think about using a pan, using a saucepan, and how you would want that to be. So obviously we want them to be cheap. That's covered there, and we want them to heat up because that's going to heat up our food. I suppose the other thing that you want is you don't want it to be too heavy. If you've got a really heavy saucepan, you're going to struggle moving that around and taking it on and off your stove. So we would look at the mass of the metal. Can't spell. So we don't want it to be too heavy, or we don't want it to be too light. We would also want to make sure that the metal it was made from wasn't going to be dangerous to us. We call that toxicity. So, we wouldn't want to make a saucepan out of lead. One, lead would be really heavy. It'd be hard to move around, and it would also be toxic. So, it might kill you if you use it. Often the lead builds up in the body. So, we would consider the toxicity of the metal. There are a couple of other things as well. You wouldn't use a group 1 metal, the alkali metals, the ones that where you put water in them, they start to react. You wouldn't want that to happen if you sort of put some water in to boil some pasta and all of a sudden they started reacting and set on fire. We wouldn't want that, so we'd probably think about the reactivity of the metal. We'd want our pan to be strong, so we'd think about the how hard the pan was or the strength of the pan. We wouldn't want a really flexible metal that would bend when we put things in it. And we wouldn't want it to rust too easily. So we'd want to think about using a metal that doesn't rust easily. So lots of points that we could have used for that one, but they're the two that I've chosen. Okay, that completes question 2. Join me in a second for question 3.